Hey there, welcome back to Short Text 331. Today I want to give you a quick example on a Fourier series. And this is one of the simplest examples you could do actually with Fourier series, and it's given by this function. So suppose you have this function. It takes on values of -1 between minus pi and 0, and it takes value 1 between 0 and pi. So of course it's a discontinuity here. That's okay. And if you think that this function is periodic, in the sense that it repeats itself after pi, so it goes back to -1 after pi, and then 1 at 2 pi, and so on and so forth, or 3 pi, then you see that this function has not just one discontinuity, but it has a whole string of discontinuities. And so the Fourier series is going to be sensitive to that somehow. So we'll get to that in a minute. So the Fourier series that we want to calculate then is given by this form that we saw in the previous video, or the one before that. So it's a0 over 2 is always our first coefficient, and then we have a sum over k from k equals 1 to infinity, and there's the ak, bk parts of the series. So one with cosine of k pi x over L, and the other one with the sine of k pi x over L. In our case, this L is pi, and so the series simplifies a little bit. We still have the a0 over 2, but now the argument of the cosine and the sine is just kx, because the L cancels with the pi. Simple as that. Now we know something else. This function is odd. It takes negative values to the left, positive values to the right, and they're exactly the same values, except that they're opposite in sign. It could have been 1 and -1. It doesn't matter which one is left and which one is right, as long as when you cross the 0, you get the opposite values, or rather the same magnitude, but with the opposite sign. And so that tells us right away that the sine part of the series is the only one that's going to survive. Okay, this cosine part is going to be 0. The cosine is always an even function here, cosine of kx, and so this has nothing to do with our function. It's going to vanish, and so is this a0, by the way. So remember, this a0 essentially encodes the average of the function over the interval. The average of this is 0, so this integral over the whole function would be this area plus this area, and so they cancel each other out. So that's definitely 0. And the same is going to be true for all the AKs. All the AKs vanish. And so we're left with the task of calculating BK. That's all we need to do. And so you should always look for these symmetries in your functions, or if you can write the function as the sum of symmetric or anti-symmetric, or rather odd and even parts and so on, because then that will simplify your calculation. So then we get to calculating the BKs. And that's just the task of doing the integral. Our function takes on values -1 between minus pi and 0, and so we put the -1. There we split the integral into two parts, from minus pi to 0, and we have -1. And then from 0 to pi, it takes on the value +1. And so we do the two integrals separately. But it's really the same integral, because this -1 is just along for the ride. It's just a constant. And so the integral of the sine kx is 1 over k cosine kx with the minus sign. So that minus sign cancels this guy. And then over here, again, the integral of sine kx is minus cosine kx divided by k. And so all we need to do is, well, let's see, we have 1 over pi, we have 1 over k cosine kx, and then evaluate between 0 and pi, minus pi here, and between 0 and pi over here. So just keep track of the signs, it's very important. So the integral here takes care of this minus sign, and it disappears down here, but here we have a +1, and so when we do the integral, we get an extra minus sign. And that actually plays a role. So let's go ahead and evaluate that and see what comes out of it. So when x is equal to 0, the cosine is 1. And so when x is equal to 0 here, the cosine is 1. And so we don't have to worry about that end. But the minus pi and pi ends are something to be a little bit careful about. So let's see. The cosine of k times minus pi is actually the same as the cosine of k pi. So actually, the value at minus pi is going to be the same as the value at pi for the cosine. And so that helps us. It means that we only need to do this part of the work once. And it turns out that the cosine of k pi is -1 to the k. You can convince yourself by drawing a diagram like I did here. So the cosine at 0 is 1. The cosine of at k equals 1 would be the cosine of pi, which is -1. And then 2 pi and 3 pi and 4 pi and so on and so forth. So every time we increase k, we go around this circle, 1/2 circle. And so for k equals 0, which is, by the way, we don't care about k equals 0. Remember that the series starts at k equals 1. If we separate this term, which in our case is 0 anyway. So then we don't really care about this case, but we care about k equals 1, and that's -1. K equals 2 is 1, and so on and so forth. And so we get exactly that this is minus 1 to the k. So for k even, result is 1, and for k odd is minus 1. And so let's go ahead and write that down. The full result corresponding to each of these terms is 1 over pi, 1 over k, 1 from the cosine of 0, minus 1 to the k from this guy. And then for the other guy, evaluating between pi and 0, we get minus 1 over pi, 1 over k, minus 1 to the k, minus 1. And so we have this minus sign here, it was written here, and then minus 1 to the k comes from evaluating at pi, and then the 1 comes from evaluating at 0, this 1 here. So now we can assemble all that, but look carefully at this. So here we have 1 over pi, 1 over k, and this thing, and here we have 1 over pi, 1 over k, and the same thing with the opposite sign. Oh, but we have an extra minus sign here. So this means that the result is really twice this. Okay, this minus sign, you can use it to flip these two terms and turn it into this. And so the result of bk is 2 over pi k times 1 minus 1 to the k. And now we look more closely at this, and we see that for k equals 0, for example, which we don't care about, this is 0. For k equals 1, this is going to give us 2. But for k equals 2, which we do care about among the even numbers, then we have the result is 0. So this is 0 for all k even. And so not only do we get rid of the AKs, we get rid of half of the BKs as well. So that's interesting. And so the BK then is 4 over pi k if k is odd. That's the result. Okay, so when k is odd, this number is 2. And so because we get a minus 1 here, and negative minus 1 is 1, and so we get a 2 for that. And so that multiplies the other 2, and we get 4 over pi k for k odd, and 0 otherwise. So we only need to sum over the odd case. And so I go ahead and parameterize that with the number n, and say that my odd numbers are 2n plus 1, and starts with n equals 0, because then I can get the 1, which I need. And so then f of x is the sum from n equals 0 to infinity, 4 over pi times my odd number times the sine of my odd number times x. And that's it. That's the result for f of x, and that's the final form of my Fourier series. If you instead had written it in terms of k, and had inserted this formula in here, that would be okay too. It would still be a correct result. It would simply mean that the every other term would vanish, right? So all the even terms would vanish. So that's fine. So if you want to write only the non-vanishing terms, then this is the result. And you can go ahead and plot that. And it's interesting to see what happens when you start adding terms. So if you add the mode with n equals, this actually should be n equals 0. So the first odd term, then you get this this orange line. By the way, the exact function is of course in blue here. It is minus 1 to the left and 1 to the right. And so the first mode, the first non-zero mode that we can add is actually just the sine of x, and it gives us this orange line here. If we add 2 non-zero modes, then you get the 1 and you get the 3. So you have the green line here. And if you add 3 non-zero terms, so the one with sine of x, sine of 3x, and sine of 5x, then you get this darker orange line, this darker orange curve. And so you see that as you add more and more terms, this really is looking like it's trying to go to my straight line here and straight line down here, which is just a mirror image of this one up here, of course. And it's trying very, very hard to do so, but it will always fail to reproduce the discontinuity here, because the value of the sine at 0, any number times 0, is always going to be 0. So this curve, this series is going to try very hard to give me the right answer here in the middle, but it's always going to fail here. And so this means that as we approach these edges close to 0 and close to pi and close to minus pi, I'm always going to see a very wild oscillation, which is actually called the Gibbs phenomenon. Okay, so as you add more and more terms in this series, you see that you will approach nicely the result in the middle, but close to the edges, close to the discontinuities that your function may have, then you will have trouble. And remember, I mentioned this before, these functions are infinitely differentiable. They're really, really nice and smooth, and so they would have a very hard time reproducing discontinuities, and that's what you're seeing then as you add more and more terms. I encourage you to do what I did here, which is grab Wolfram Alpha or Mathematica or whatever. And by the way, I'm not paid by any of them. It's just a tool I use. and go ahead and plot this and add more and more terms. You can easily add 10, 20 terms and see exactly that as your function, your construction will approach the function, the target function that has our discontinuity, but it will fail at the points where that discontinuity happens. And so it is said then that this type of series, when it converges to the right function almost everywhere, where the almost everywhere is to simply to say, well, we have to be careful that we're really not going to approach the target function at those points where it is discontinuous. And that's it. That's all I have for you today for this example. I hope you enjoyed this video. If you did, please like and subscribe. And as always, if you're looking for a tutor in physics or math, in English or in Spanish, you can contact me at shorttext331@gmail.com, or you can leave a comment in the comment section below and I will get back to you. And I will see you next time.